So here we are in section 4.3, acid and base reactions. Acids are substances that form H pluses or form H's that have lost an electron. Acids are known as H plus donors, and in H plus, if you look on the periodic table, hydrogen normally has one electron, but when it loses its electron, it has 0 electrons left. So the only thing remaining of that hydrogen that has lost an electron is a proton. And so H plus is also known as a proton. And so acids are sometimes known as proton donors, or ones that give away hydrogen ions. Bases accept hydrogens. They're things that take in H pluses or accept protons. They also are known as producers of hydroxide ion in solution. And if you look at an example reaction of a base, you can see that water will react with this base known as ammonia, and it will form hydroxide ion on the right-hand side. And you'll notice that NH3 becomes NH4 with a little plus sign right here, and therefore it accepted a hydrogen ion from H2O. Illustrating this further, we could write HOH right here, and then we could put NH3 like this in its structural formula, and one of the H's is given to the NH3, and then we can see it forms the NH4 over here, and it forms the hydroxide ion OH right here that has a minus sign. So in acid and base chemistry, lots of times we want to know the strong acids versus the weak acids, or the strong bases versus the weak bases. And you learned this a couple of video casts ago, that the strong acids, you memorized them, Hyber, Hickel, High, Hono, Hickelo, and then H2SO4. And these are on this page in your textbook if you're using the 13th edition, and there'll be a quiz, a memorization quiz on those. Everything else is a weak acid. The strongs fully dissociate or ionize, and the weaks only a little bit. The strong bases, of course, are the hydroxides of lithium, sodium, potassium, rubidium, cesium, calcium, strontium, and barium, and you should have those memorized as well, and you should be able to write those formulas, and there'll be a quiz on those as well. So doing it as particles is also valuable. There are 3 acids in this image that I'm going to put on the screen, and we want to rank this HX acid, this HY acid, and this HZ acid from weakest to strongest. So let's zoom in on this picture and let's take a look at these. It says the following diagrams represent aqueous solutions. The water molecules are omitted for clarity, so it's assumed that they're aqueous. Rank the acids from strongest to weakest. So, if you remember, strong acids are one that completely ionize or dissociate or break apart in solution. Weak ones are ones that don't break apart very much. So if you categorize each one of these, which one has the most pluses and minuses? Hopefully you said HY. HY would be the strongest acid because it's completely dissociated or completely broken up or completely ionized into pluses and minuses. How about between the other two? Well, if you look at this one, there's 3 pluses and 3 minuses. If you look at this one, there's only 2 pluses and 2 minuses. The one that breaks apart the most is the strongest, and therefore the one with 3 would be the next strongest acid, and the one with only 2 would be the weakest acid. So ranking them from weakest to strongest would be HX, then HZ, then HY being the strongest. Hopefully that's helpful in illustrating or understanding what's actually happening, because when acids or bases that are strong dissolve, they form lots and lots of ions, and we want to illustrate those. Remember, the strongs are the ones that are split. Those are the ones that ionize or dissolve or completely dissociate. So acid and bases react in what are called neutralization reactions. They neutralize one another. So an acid plus a base makes water and something called a salt. A salt is something that has a cation from a base and an anion from an acid. Remember, cations are positive and anions are negative. Here's an example reaction of a neutralization reaction. Magnesium hydroxide would be our base because it contains OH. HCl would be our acid. It's a strong acid. And then what happens is we exchange the positive ions, just like we did in metathesis or double replacement or reactions that formed a solid last video cast. And we see that magnesium then goes and combines with chlorine. Remember that magnesium's +2 and chlorine's -1. If you forgot that, look at your periodic table. Magnesium's +2, chlorine's -1. And so we crisscross those or drop them and switch them. Drop the charges and then switch the charges. And then it'll form water, H with OH over here. And to balance it, we put a 2 here and a 2 here. From this, we want to write what is called the ionic or net ionic equation. And to do this, we have to go through the same process we did for precipitation reactions. If it's a pure solid, leave it together. So we just write magnesium hydroxide. If it's a strong acid or a strong base or a strong electrolyte, we want to split it. And so we would split this up into 2H plus and 2Cl minus. And then on the right side over here, if it's aqueous and it's a strong electrolyte, then we can split it up. And since MgCl2 would be a chloride, and all chlorides are soluble, and it's an ionic compound, we would say, yes, it's a strong electrolyte, and therefore we would split it up in Mg plus 2 and 2 Cl minuses. Notice how the 2 goes out here to make sure that there's 2 Cl minus formulas. And then water, of course, is all nonmetals, and it's a molecular substance, so I just keep it together. Now, if there's anything the same on both sides, we cancel that, so the 2 Cl minuses would go away, and then my net ionic equation would be MgOH2 plus 2H plus goes to Mg plus 2 plus 2HOH. These ions right here would be known as the spectator ions, or ones that just watch the reaction happen. Let's do a second sample, sample exercise 4.7. And if you don't have a textbook in front of you, I'll put the question out in front of you. It says, for the reaction between aqueous solutions of acetic acid and barium hydroxide, write the balanced molecular equation, the complete ionic, and the net ionic. So acetic acid and barium hydroxide. All right, let's see if we can do that one. Let's do all the parts of it. So acetic acid is written two different ways. We'll write it this way, HC2H3O2, and then barium hydroxide is BaOH2, and it told us that both are aqueous solutions, so we'll put AQ down below it, and then we'll draw an arrow. Now to get the products, remember we swapped the cations, and so we swapped the H with the Ba, and it's a neutralization reaction. Notice this is an acid, it told you that in the question, and barium hydroxide is one from the B on the periodic table. Barium's right here, and it's a hydroxide, meaning it's a strong base. So the H and the OH will come together to form water, and then we'll have barium together with the C2H3O2 ion over here on the right-hand side, the acetate ion. Now be careful with this and make sure that you get the charges correct. Barium's +2, and if you forgot, acetate up here is -1. And so with a +2 here and -1 here, we'll have to illustrate that there's 2 of them by putting a small 2 down below here. Now balance the chemical reactions. We need 2 of them here and 2 of them right here. So then we've got the correct number of hydrogens, and we've got 2 acetates and 2 acetates. This is the molecular equation. Next, it asks us to write the complete ionic equation. And to write the ionic equation, we have to go through and ask if each one of these species is strong. And if it's strong, we split it or write it as its ions. This C2H3O2 is not one of the strong acids you memorized, and therefore it must be a weak acid, so we just leave it together. Weaks and non-electrolytes always stay together. Weaks and non-electrolytes always stay together. Barium hydroxide is one of the strong bases that you learned. You memorized this. It's in the B on the periodic table, so we would split this up to be Ba+2 and 2 OH minuses, because there's a 2 right here. Water, of course, is molecular, so we keep that together. It's 2HOH. And then over here on this side, we need to look on our solubility rules, because remember we made a salt right here, or an ionic compound, and it's a solubility rules table entity, and we want to look and see if acetates are soluble, and look at that, they can be soluble right here, and since it's soluble and an ionic compound contains a positive ion and a negative ion, then we would split it up. And so I write Ba with a little +2 and 2 C2H3O2 minus. This is our complete ionic equation. Notice how the 2 went out in front here to illustrate there's 2 of those ions. Lastly, we want to write the net ionic equation, and we notice that the barium ions are just spectators. They're not part of the reaction. They just watch the reaction happen. And so we recopy everything else except the barium ions. There's an example problem of a strong base plus a weak acid neutralization reaction. Lastly, before we're done, there are a few special neutralization reactions that form gases. This is an acid plus a special anion on some type of salt or base that forms a gas. These special anions are sulfide, carbonate, hydrogen carbonate, also known as bicarbonate, sulfite, and hydrogen sulfite, also known as bisulfite. So here's one example problem. Hydrochloric acid plus sodium sulfide. Swap the cations. We get Na together with Cl. Sodium's +1, chlorine's -1. And then H together with S. Hydrogen, of course, is +1, and sulfur is usually -2, and so it needs to be H2S. H2S is a gas. H2S is usually the gas that's associated with really smelly, rotten egg stink, and so this is hydrogen sulfide gas. To balance this reaction, I think I need a 2 here, and then I could go on, I could write the ionic and the net ionic equation for that. But notice this is a gas, and so that would never split up, whereas this would split because it's soluble, this would split because it contains Na, and this would split because it is a strong acid. One last example, HCl, or hydrochloric acid, plus a hydrogen carbonate. So now swap the cations again, H, and then I'll have H2CO3 because it goes with it, 2 8 and H and H makes 2. And then I'd have Na together with Cl, so I'd make some NaCl over here on the right side. Balancing this reaction, oh, it's already balanced. And this right here is very special because this formation of H2CO3 decomposes. And it decomposes immediately when it forms into water and CO2 gas. And so when you write the net ionic or just the regular molecular formula, you technically never write H2CO3 you only write these two species because it's a special gas-forming reaction. And so if I wrote the complete molecular equation, it should be HCl plus NaHCO3 forms water, carbon dioxide gas, and NaCl. I could go through and write the ionic and the net ionic for this, split this one, split this because it's got Na in it, as long as it's aqueous. Remember, if it's a solid, keep it together. Pure water stays together, CO2 stays together because it's a gas, and NaCl would split up into its ions because it's aqueous as well. Good luck with your acid-base reactions.